talk about what is green building. So what are we going to do here? We're going to describe or discuss some of the characteristics of green or sustainable architecture. I'm hoping to talk about this both from the point of view of an architect or designer and also from the point of view of those on the construction side of the business, project managers, general contractors, tradespeople. We have all of the above in this class. I'm also using the terms green and sustainable somewhat interchangeably. Hopefully I'll touch on why this is important, and this will really be geared for residential construction. We'll focus on the building envelope. That's certainly the biggest driver of making residential buildings more efficient. We'll talk about review windows and insulation material. I think we touched on some of these topics way back when we looked at materials in Unit 7. We'll look at some methods of improving the performance of the walls, what I'll call high performance wall construction. Again, this is not meant to be exhaustive. We're really just touching on things, and you'll learn more about these in subsequent classes in our program here. Good evening, George. We're just getting going. We'll talk about the Passive House Standard. That is a standard for high performance building construction. And then we'll look at waste in the construction process. What are some things that you can do if you are the contractor or project manager or superintendent or a tradesman out in the field? What are some of the things that you can do to contribute to reducing the materials usage for construction? Sorry for a lot of words on the slide here. This is always the challenge when you make these things up. You want to put a lot of information on a slide, but some of the attributes of sustainable architecture: number one, we want them to have a healthful interior environment, right? A good place for us to be. We spend a lot of time inside in our homes, in our classrooms, in our places of work. If you're like me, in the time of COVID, right, I spent an awful lot of time sitting in my home office here, either working or teaching. So we want to make sure that we are not building with substances that are toxic or emit toxic substances. We don't want things that off gas. We want things to be not harmful to human health. We want our buildings to be efficient in their use of resources, heating and cooling and lighting and water. We want to make sure that the materials that we are using in our building, we're minimizing the impact of those materials on the global environment, that we're, say, using sustainable materials if possible, harvesting wood responsibly, not using materials that are produced from a toxic or a polluting form of production. We're going to make sure that our buildings are well designed, that they're pleasing, that they're beautiful, that they're enjoyable, that they're also long lasting and are maintainable, right? So we want to try to achieve all these things in our either design or construction of buildings. Right, so what are some of the key features of green buildings? The most obvious one is location. Where do we build or where do we renovate? Ideally, we want to build near other existing buildings. We want to, if possible, reuse an existing site or an existing building. We don't want to build out in a natural area. We don't want to, take away agricultural land or habitat. Ideally, we want to locate near public transportation, right? We've made an investment in infrastructure, right? We've talked about infrastructure this semester, right? Electrical systems, water supply, sewers, public transportation, roads, electricity, right? We want to build places where all that infrastructure already exists rather than someplace that's going to drive additional sprawl. So location matters. We want our buildings to be energy efficient. We want to minimize the energy that they use. And I'm using the term integrated design. And integrated design means that we're not just going to plop solar panels on an otherwise inefficient structure. We're going to think about all the things that go into making a building efficient: the wall construction, the insulation, the windows, the lighting, the equipment. Do all those things make the building as efficient as possible first by design, and then from there we can look at on-site renewables. We want our buildings to be water efficient as well. You know, we think about energy efficiency. We don't always think about water efficiency. We want to minimize the use of domestic water supply from off-site. You know, minimize how much water is being used. Ideally, we want to retain or manage the rainwater that falls on the site. Again, we'll learn about this more in ARC 110 and other classes, but you know, we want to, you know, the stormwater that leaves our roof and our hardscape ends up being a source of pollution that someone else has to deal with. We want to try to manage that on site, and if possible, minimize the discharge of wastewater to the sewer. This is actually a picture. This is from years and years ago. This is the roof, or the green roof, on the city side of City Hall in downtown Chicago. I don't know if it's still this way. I went up there years ago when, this is now 2 mayors ago, when I was going to say the former mayor, but now it's 2 mayors ago, Mayor Daley. You know, he, for some reason, had a lot of green initiatives in the city, and one of which was to do a green roof on City Hall. I don't know whether that's still there or not, but it was pretty cool going up there at one point. This is, I don't know, probably 12 or 15 years ago that I was up there. Good evening, Christopher. Thanks for joining. Talking about attributes or features of green buildings. We want our buildings to be wise in their use of materials. So possibly we want to use recycled or reused materials. We want to build with materials that are renewable or rapidly renewable. If possible, build with materials that are obtained locally or near the building site. You know, we want to avoid having to transport or truck the materials that we're using to build our house from, you know, across the country, or having us have them in a container shipped over here from China, right? We want to shorten our supply chain. I think if we learn nothing else in the pandemic here, is that we need to think again about where things come from and what our supply chains look like, and try to shorten up those supply chains. And then we certainly want to use materials that are not toxic in their production or in their use. We want our buildings to be healthy places for us, for humans, for people. We want them to be well ventilated so the indoor air is fresh. I probably should have put my little buildings in the time of COVID. We also, you know, as we start to go back to our classrooms and our offices and our places of employment, we're going to be concerned about ventilation and filtration, right? Those are things that have always been important, but they're going to be even more so to make sure that we, you know, control the spread of COVID in the interior environment. We like to see daylight and views. You know, that makes the occupants feel more connected to the outside world. We certainly want to make sure that non-toxic products are used for cleaning, and non-toxic products are used in all the things that go into a building, the paints, the finishes, pest control, maintenance. We want to keep all those toxins out of the building. Good evening, Ayana. Thanks for joining. If possible, we want to build with renewable building materials, materials that are found in nature and produced in a way that their availability and quality does not diminish over time, right? So obviously wood is a renewable building material, but it's a renewable building material if the forests that wood comes from, are managed sustainably, right? We built all the wood from our fair city of Chicago came from Wisconsin or Michigan, right in the late 19th or early 20th century. We, cut down lots of trees in those states to provide the wood to build our city. Not sure how much of that was done sustainably. Also, there's other natural materials that can be used in building construction: straw, hemp, cotton, wheat, rubber, bamboo, cork. Those are all natural materials that are possible components of a building, or of a green or sustainable building. Another source of materials for a building come from recycled building materials, right? Materials from a source that is not brand new. That can be other buildings. It can be industrial buildings, shipping containers, recycled plastics. All sorts of possibilities for things that can go into our buildings and reducing their material footprint or material impact. Right, as I said before, good buildings don't exist in isolation. Again, this is the responsibility of the designer to make sure that the building as it's designed relates to its site and the surrounding community, right? That it doesn't sit in isolation, that it's not an eyesore, that again, it's a beautiful place that people want to be. That's the architect's role in green building. Another possible way that we can, reduce the materials use for building is what's called adaptive reuse. If they're a building that no longer serves or is no longer used for its original purpose, it can be adapted to serve new uses, right? This is far more efficient, uses far less resources than tearing down something and building something brand new, right? If we go to the west side of Chicago, there's plenty of old loft buildings that have been repurposed into condominiums and apartments and shopping, et cetera, right? It was made a lot more sense to reuse and repurpose those buildings than it did to tear them down and try to build new, right? Good solid, high quality construction can be reused or repurposed. So again, what are some of the attributes of green or sustainable architecture, right? We're a healthy interior environment. It's efficient in its use of resources. We're using ecologically benign, right? Benign means not harmful, right? Relates to its site, and it's well designed, and well designed in the broader sense of being easy to maintain, long lasting, high quality, right? That's another way that we can reduce the environmental impact or the resource use of the buildings, is that we can build well. We can build for things that are going to last a long time, right? That's something that the architect can do, and it's also something that the construction team can do, right? Build good, high quality buildings that last a long time. Again, here's another set of slides kind of getting after the same point. right? Sustainable architecture refers to the practice of designing buildings which create living environments that work to minimize the human use of resources, right? That's what we're trying to do here is have buildings that use less resources. Why is that? Well, resources are scarce. You know, we have an issue with climate change, right? We're burning too much fossil fuels. We have to, we in the construction profession have to be way more thoughtful about what we do. So that resource use is reflected both in the materials that are used to construct the building, as well as materials that are used to heat and cool and maintain the building. So all those things we need to look at. We need to look at ways of minimizing or reducing all that resource use in buildings. Let's talk a little bit about windows, right? I think this might have been a slide from one of the lectures way back when. Again, if we are designing in our climate, we have a number of options as either the architect or designer to specify, or as the contractor or tradespeople to install, right? We have high performance windows that can reduce the heating and cooling loads in our buildings. Right, so what are some of the things that make a window energy efficient? Has to do with the quality of the frame, multiple panes of glass, 2 panes of glass or 3 panes of glass, double glazed or triple glazed windows. And then we can play around with the surfaces of those, what's on the surface of that glass and what gases fill the space between those panes of glass, right? These are the things that go into high performance windows, right? We typically will fill that space between our double or triple panes with argon or some gas like that, which improves the thermal characteristics of the building. And we can put low E or low emittance coatings on some of those surfaces as well. All those things improve the performance of windows, right? Those are things that we've learned how to do here, gotten better at this in the last 15 or 20 years. Right, here's another example again of a window with insulating glass or double pane or thermal pane glass. You see there's a lot of detailing there in terms of how the window is put together. So again, we all will have a role to play here. The architect or the designer has to specify that window, and the tradespeople have to install it carefully and thoughtfully to make sure that it actually achieves the performance that the architect had in mind when he or she specified it. But again, we look at a couple of things. I think someone asked me this question last week or about R value and U value, right? When we look at windows, windows, their heat loss is rated in the U value or U factor, right? So a smaller number is better, lower is better, less heat loss. SHGC, solar heat gain coefficient, that has to do with how much of the radiance, how much of the sun that's shining on that window is emitted to the building as heat. So again, lower is better, less heat gain. We also have to look at how well can we see through the window, right? We have, like lots of things in our business, there's always trade-offs, right? If you improve one factor, sometimes there's a trade-off someplace else. So we obviously want to be able to see through the window, right? Visible transmittance, how well can you see through the window? Higher is better, we can see more clearly. And we also want to look at the air infiltration or air leakage. In this case, lower is better, less heat loss. So as designers and contractors, we have a number of different performance factors that we have to balance in our selection and installation of windows. So again, the same, just like you don't build the same building in multiple parts of the country, you're not going to select the same window necessarily. Certainly as you are in the northern climates, right, in Chicago, us in blue there, or in Duluth, Minnesota, you're going to pick a window that has a low U factor and not necessarily be concerned about the solar heat gain coefficient. Obviously, if the inverse is true, if you're in the southern part of the country, you see red hot down there in Phoenix and Tucson and Houston and Miami, right? You have different considerations. If you're in a warmer climate, you're going to pick a window that has more to do with its solar heat gain performance. So that was windows. We have talked about insulation, but certainly it bears reminding and repeating. Right, we use insulation to reduce heat gain or heat loss. Right, heat loss is what happens in the winter time when it's warm in the house and cold outside. Heat wants to move from an area of higher temperature to lower temperature, so it's going to tend to want to leave the structure in the winter time, or the opposite is going to happen in the summertime when you're trying to keep the house cool, or relatively cool inside, and it's 90-some degrees outside, right? Then the heat is flowing in the opposite direction. So we have insulation to reduce that rate of heat transfer, right? And the R value is what we use to describe that heat transfer characteristics of the materials. Once again, R value, it's easy for us to think of as Americans. Bigger is better. A larger R value is better. We have a number of different general classes of insulating materials. You know, flexible, bats or blankets, blown in, spray foam, or rigid. We'll see some pictures of all of those. Right. R value is what we use to measure the performance characteristics of an insulation or a composite wall or composite roof. Again, the higher value, the greater the insulating effectiveness, the better it's going to be in terms of its characteristics. Other way around, right? R value is typically what we use for solid materials for insulation and wall construction. U value or U factor is the inverse. So U equals 1 over R. That's typically, as we saw, what we use to rate windows and doors. The building codes use this map of climate zones. And as we'll see, the requirements in the building codes for levels of insulation and performance of windows vary by climate zone, which makes sense. Again, we go from number 1 there, subtropical Miami, all the way up to frigid Duluth. So from 1 to 7, the building codes or the model codes will have different requirements for the levels of insulation and the performance of windows. So again, this is, I believe this is, I took this out of the IRC, or the International Residential Code. The same thing will also be in the IECC, International Energy Conservation Code. Remember, we talked about the I codes early in the semester. So the IRC and the IECC have this table of insulation and fenestration, right? Fenestration is the fancy way of saying windows and skylights, glazing, right? So those building envelope requirements vary by climate zone. And again, this is in a building code. This is building code language. So the building code specifies the minimum requirements. But if we are really going to try to make our buildings high performance buildings, then we want to do better than what the code minimum is, right? Code is minimum requirements. We as architects or construction professionals want to try to do better than what is code minimum. Same thing, here's those same climate zones for Illinois. The climate zones are all broken down by county. So depending on what county you're in, the requirements may vary, right? If you happen to have an architectural practice where you're designing buildings both in St. Louis and Chicago, you might have slightly different requirements that apply, because I'm pretty sure that St. Louis is in climate zone 4 and we're in climate zone 5 here up here in Chicago. So again, why do we insulate? We insulate because we have losses that take place in all the various components of the building envelope, right? The building envelope is a thing that separates us and our comfort from the outside. So we lose heat from the roof, the walls, and all these other places that you see, from ventilation and drafts, right? Maybe this must have been written in England, because they're spelling drafts in a funny way, right? Same thing. Here's all the various places that we have to think about our insulation and our insulation details. And again, this is both parts of the construction team need to think about this. You know, the architect in what you design and how you detail and specify, and the construction team to make sure that you carry out those details and execute the work in the field to achieve the intent of the designer. Again, here's our fiberglass bats. This would be a flexible insulation material made to fit between stud walls. And we see our friendly pink panther there, R19. So that's a fairly decent level of insulation, made for a 2x6 wall, or nominal 5.5 inches deep. Here's spray foam insulation. Again, this is going to be more expensive, but you will achieve better thermal performance, higher R value, and certainly works better if those stud spaces are irregularly shaped and don't necessarily lend themselves to fiberglass bats. Right, here's rigid insulation. Again, we've seen that as we've looked at details these past few weeks, looked at foundation details and floor slab details. We've seen rigid insulation there. I think we had some Sullivan questions about the insulation of the basement walls in Sullivan. That was R6 rigid board, if I recall correctly. Right, here is blown-in insulation. We can quite often see this in the attic, and also if we are retrofitting, right? The person up there looks like they are retrofitting or insulating an existing structure. So again, we have to think about not only the new buildings that we build, but all the existing buildings that need to be made more efficient. Again, we in the construction business have lots of opportunity here to build high quality, good new buildings, and also to improve and retrofit all the existing buildings to make them more efficient as well, right? Plenty of work for all of us. What are some of the tools that we use to judge the quality of our work, right? We can use this infrared camera or thermographic camera to look at the quality of insulation. This might be a tool that an energy auditor uses Again, energy auditing is a career opportunity that's open to us, construction professionals, right? We can learn how to look at existing structures and figure out ways to make them more efficient, right? A camera like this would be a tool that an energy auditor would use. It might also be a tool that a contractor or general contractor might use to check on the work of their insulation subcontractor, or a tool that the architect might use to check to see if the construction team has delivered on the quality of construction and the detailing that was specified. Right? You see thermography as a quality control tool to ensure that insulation has been installed correctly. Other thing we need to keep in mind as we are both designing and building and retrofitting homes, we also have to look at air infiltration, right? That's all the sources of leakage, all these places where dissimilar materials come together. We have the potential for air leakage. And I always like to say that, infiltration is uncontrolled air leakage and ventilation is controlled air movement. So as we make more efficient structures, as we get better in terms of the quality of both our detailing and our execution in the field, we reduce air infiltration, that we might have to substitute some ventilation to make sure that we continue to maintain a healthy indoor environment. Here's another, these are diagnostic tools. Here's another image of a thermographic camera. The other diagnostic tool here is what's called a blower door. Again, this is something that energy auditors can use to check on the performance of an existing structure. It's also something that insulation contractors use to check on the quality of their work. Right? Years ago, Francis and I had someone come in and insulate our home, and at the end of the job, they did a blower door test, and they could all tell how much tighter that they had made, how much they had improved the air tightness of our home by virtue of the work they did with insulation and air sealing. Right. So those two tools put together would help an energy auditor visualize areas of air leakage that they can correct. Right. Things that we as construction professionals can do depending on the kind of work we want to do, but certainly opportunities to make, as I say, make existing buildings more efficient. Right, I think in all the examples of construction we've looked at here in Sullivan and Marseille, our residential buildings, we've seen them as 2x4 construction with some kind of sheathing, right? That 2x4 is something that has, relatively speaking, a lot of heat loss or heat gain. And if you take one of those thermographic images of a typical wood frame house, you're going to see something like this, right? So again, if we want to make this structure more efficient, right, we've put insulation between the studs. Now we have to think about ways of reducing the heat loss or heat gain through the structural member itself. That's called thermal bridging, right? We want to look at ways of reducing thermal bridging, of making our walls more efficient. A couple different ways we can do it. Again, I'm just going to touch on various techniques. We'll certainly cover these in more detail depending on the classes you take in our program here, but we can stagger the studs in our wall. So we create more space for insulation. And now we've also reduced that thermal bridging, right? Because we no longer have a straight through path or heat loss or heat gain through that framing member, through that stud. Right, again, here's another example of a staggered stud wall. We can make that wall thicker. As we make the wall thicker, we are giving ourselves more space for insulation and improving the thermal performance of that wall. This is something called a double stud wall. Again, the same idea. Right? We have a structural wall, and then we have a separate non-structural wall, and the space between the two gives us additional space for insulation, additional ability to make the building more efficient. Right, so I think when we looked at our Sullivan or Marseille, we had 2x4 framing members, and I think probably R11 or R13 wall insulation. We just looked at R19 and a 2x6 wall. If we're using some of these techniques of staggered stud or double stud wall, we can get a much higher R value. We can get up to something like R38, and we also have tackled that problem of thermal bridging. If we really want to take things all the way, we can design and build houses according to the passive house standard. This is a standard for high performance buildings, very high levels of insulation, triple glazed windows, low levels of air leakage, right? We've drastically reduced infiltration, both by the detailing of the architect and also by the execution of the folks in the field, the construction team, the tradespeople, the carpenters, right? Everyone has a role to play in making a high performance building. So if we reduce the infiltration, then we have to substitute ventilation, right? Infiltration is uncontrolled, ventilation is controlled air exchange. And then if we are really stringent about the performance of the building envelope, we get to a point where solar heat from modest amounts of glazing and internal gains can heat the house. What does internal gains mean? Internal gains means the heat that all the human beings in the house and the appliances, the refrigerator, the cooking, right? All those things contribute heat to the house. Normally, you don't really think about that because a lot of that heat is being lost through poorly insulated walls. But if we really tighten up the building envelope, if we take a systems or an integrated design approach, then we get to the point where we can heat the home for the most part with solar and internal gains, right? Maximize gains, minimize losses. Right, here's sorry, this is a little hard to see right. So again, the passive house standard, high levels of insulation, high performance windows, airtight construction details, air-to-air heat recovery. Again, this is our ventilation. So we exhaust stale air from the house, and we use that exhaust air to preheat fresh air supply that's coming into the house. So we have a controlled source of ventilation. So again, if this is done well, then modest glazing and internal heat gain can heat the house. Right, this is where our industry is going in terms of residential construction. Hopefully they're going in this direction. Right, again, here's some details. Right, our 60 walls, our 85 roof, right? Those are freaky high levels of performance. But again, this is what passive house is moving towards. Again, I've been in this business for a long time. When I first got into doing energy efficiency, right, this is kind of what some of our structures look like, a little bit garish, right, kind of call attention to itself, right? That's not necessarily what we want to do. That's not really in context. But we did this because we hadn't really thought about the whole system. We didn't make the building envelope efficient enough, so we needed a lot of glazing to heat the house. But now if we have a good high performance building envelope, we can make a house that doesn't look that much different than its neighbors, right? It doesn't scream, oh, look at me, I'm different, right? It fits in well, right? That house there would fit in well in any of the communities that we live or work in. If we are in a cold climate, we might need a little more glazing area, right? I think this is, if I remember correctly, this is a house up in Wisconsin someplace, right? So again, we need a little more glazing to passively heat in this climate. And you see that there's a shading element there, right, to make sure that we control the solar gain. But again, all things that we can, techniques that we can use, techniques that are well understood now. And again, we can employ them whether we're the architect or the tradespeople or the general contractor, right? All the things that we as a team can do to make more efficient homes. So again, better design, rigorous attention to the building envelope, and system performance allows for more design flexibility, right? If we're rigorous about the building envelope, then the architect or the designer is again freed to make a beautiful looking, nice looking house, right? Doesn't have to do that. He or she can produce a design that looks like that, something that the architect can say, wow, I did a great job. I designed a beautiful house. Right, so if we lower the loads, we have less aperture area. Aperture area is the opening of all that glazing. The other important factors is we have to think about building smaller and building more compact, right? That's part of what the designer, the architect has to think about, right? These houses that are perhaps smaller, more compact, more higher quality, right? That's part of the way that we get to higher performance. I know that's a little hard for people to wrap their heads around, right? We're Americans. We think we deserve to have a big house, but that desire is kind of coming into conflict with the requirements of having higher performance construction. I'm actually going to, I posted a document. Yes, Nicole.
Quick question about the aperture area. So you're saying that we want to achieve fewer windows and openings, glass openings?
No, we want to have, we don't necessarily want to have the, if you pardon we don't want to have the tail wagging the dog, right? We want to have a design that has normal amounts, quote unquote, normal amounts of glazing, and still have that glazing capture enough sunlight to heat the house. That's what I'm, right?
Thank you.
You're very welcome. Yeah, I mean, we don't want to eliminate windows, right? We want to have windows. First of all, the codes have minimum requirements for light and for natural light and ventilation in any habitable room, right? So we have code minimums we have to meet. And in addition, right, having windows in our homes is pleasant. It's delightful. We just want to make sure that we if we have a high performing building envelope, then the architect or the designer has more flexibility in how they achieve their code minimums and create a nice design and make it high performance. Couple of YouTube here. I'm actually gonna, I have a document up on the on Blackboard that has some of these links. I know I'm going to try to get through this and then get to the Frank Lloyd Wright Unity Temple thing. So um, this one here, I don't know, runs 10 minutes or so, but it's about a factory in Maine where they build prefabricated high performance houses. I'm always of the mind that prefabrication is something we should be doing, but the industry hasn't quite gone in that direction yet. But again, I'll put these links up there in case you're interested. So again, the other thing to think about, we just talked about the building envelope. We also have to look at the efficiency of all the systems, heating and cooling systems that are still there, right? They'll be smaller. They won't need to be as large because we've made the structure efficient. So we have to look at furnace efficiency. We talked about AFUE a couple of weeks ago when we were looking at mechanical systems. We talked about SEER, or seasonal energy efficiency rating, for air conditioners. So again, higher SEER is better. Higher AFUE is better, more efficient. The code will have minimum efficiencies, and we want to do better than the minimums in the building code. Right? We looked also at appliance efficiencies. Right? This would be the efficiency of our television and our washing machine and dryer and microwave, et cetera, right? Those can all be chosen thoughtfully and carefully to reduce energy consumption as well. I drove around one time and I took pictures of just to show that people are doing renewables here in my fair village of Oak Park. I took a bunch of slides here, and I know as I've walked around more recently, I've seen a lot more people that have put up solar in Oak Park. It's pretty interesting. I'm sure hopefully that's happening in other communities as well. Okay, we've talked about the building envelope here, which, as we saw, has to do with both the designer as well as the construction team. And now we're going to look at resource uses in the construction process. But let's do this. I'm not going to get through this all here. So let's take a 10-minute break or so. We'll get back together at a couple minutes after the hour, and I'll finish this up, and then I'll start playing the video on Unity Temple. So any questions? Okay, so we'll hold this thought here, and we'll get back together again in 10 minutes or so. Thanks.